Hi, welcome once again to our Math as a Second Language workshop. And I'm hoping that by now you've had time to really appreciate the journey from cavemen writing on the walls, drawing pictures, through scientific notation, exponential notation. But the real beauty of place value, as beautiful as it was to see how it developed, is how useful it is in doing arithmetic. And that's what we're going to do, starting with today's lesson or lecture. What we're going to do is to look at how place value allows us to do terribly complex things in a very, very simple and easy to visualize way. There is some kind of a warning that as you advance from one level to another, and things get better and there's more you can do, you also start to see what the next obstacles are. And there is one huge problem that comes up in using place value notation. By huge problem, I mean something that is huge if we don't take care of it, but it's relatively easy to take care of. And the easiest way to do that is, let me go back to the sand reckoner. And we have here what? We have on the sand reckoner 5 on the tens line, 6, 8, 10, 12, 14 on the ones line. Now, as we look at this, there's no confusion. We can see there are 5 tens and 14 ones. What happens, however, if all we saw was the 5, 1, 4? You see, when I leave out the denominations, this can be very confusing. In other words, looking at this, is this really 514 or is it 5 tens and 14 ones? And if I wanted to tell you that it was 5 tens and 14 ones, I would have to put the 1 and the 4 in parentheses, because everything in parentheses is treated as one number, and we would see this as 14 ones and 5 tens. Now, you might wonder, why am I making such a big deal out of this? Well, look what happens when we try to add using place value. Let's suppose I'm teaching in the early elementary grades, and I give a youngster two two-digit numbers to add. Let's say 34 and 25. He says 5 and 4 are 9. 2 and 3 are 5, gets the answer as 59, which happens to be the right answer. The problem is, he might have got this by the wrong method. This is why I emphasize that have the student say 5 ones plus 4 ones are 9 ones, 2 tens plus 3 tens are 5 tens, because there's a good chance that what the youngster did was he treated this as 2 single-digit addition problems. He said 3 plus 2 is 5, and 4 plus 5 is 9. And what would have happened if he did this is that when he saw a problem like this, he would say 2 plus 3 is 5, and 5 plus 9 is 14, and he would write the answer like this. Now, what happens is that the way this stands, it's now ambiguous. But remember, if he said 5 ones and 9 ones are 14 ones, and we can think of this in terms of money because kids like that better. Think of this as being $1 bills, and this as being $10 bills. See, if you have 3 tens and 9 ones, and somebody gives you 2 tens and 5 ones, what do you have altogether now? You have 14 ones and 5 tens. Now, if you wanted to, you could say what? I'll trade in 10 of my ones for a $10 bill. In other words, the sequence of digits 5, 1, 4, and 6, 4 look different, but 5 tens and 14 ones is the same amount as 6 tens and 4 ones. Now, what we do then, in order to avoid confusion, we don't want to have to write numbers like this. So we say, okay, when we're using place value, we will agree to only use a single digit per place value column. Now, again, look at how complicated it might be if we allowed more than 1 digit per place value column. Look, for example, at the sequence 1, 2, 3, 4. The usual way to read this is 1,234. It's as if we group the numbers 1 digit per column. See, everything inside parentheses is considered as one number. But what if we did this? This would say what? You have 34 ones and 12 tens. 12 tens is 120. 34 ones is 34. Now the number would be 154. Or you could have said, what if I had 4 ones, 23 tens, and 100? You'd have 100. 23 tens is 230. 4 ones is 4. You'd have 100 plus 230 plus 4. That would be 334. Or you might say, what if I had 234 ones and 110? That would be 110, 234 ones would be 10 plus 234. That would equal 244. Look at all the different ways that this could be interpreted if we didn't have some kind of a rule to tell us that we're limiting everything to 1 digit per place value column, okay? That's going to be our tradition from now on. Once we do that, here is where the beauty of place value really comes in. Let's suppose we wanted to add, and why we would want to do this, I don't know, but that doesn't really matter for the sake of argument here. This is what? Units, thousands, millions, billions. You have 234 billion, 267 million, 580,294, and you want to add to that 352 billion, 312 million, 219,602. Well, I mean, look at just try to visualize that in terms of tally marks, or even Roman numerals, or even the abacus, whatever you want to look at this as. This is a huge problem. Now, one other thing I'd like to mention here, look at the problem here. What is the likelihood that you've ever added exactly these two numbers together? The beauty of a mathematical algorithm, an algorithm is just a fancy word for a recipe, is that it's a technique where once you understand it, it doesn't matter what numbers are given. What do we usually say? 2 plus 4 is 6, 0 plus 9 is 9, 6 plus 2 is 8, 9 plus 0 is 9, 1 plus 8 is 9, 2 plus 5 is 7, 2 plus 7 is 9, 1 plus 6 is 7, 3 plus 2 is 5, 2 plus 4 is 6, 5 plus 3 is 8, 2 plus 3 is 5. And I hope this sounded like a long, long chain, because what it emphasizes is the difference between difficult and tedious. We took two 12-digit numbers and replaced them by 12 single-digit additions. And look at how quickly we got the answer this way. This is the beauty of place value. Not just that it's a nice way to write numbers, but it's also a nice way to do arithmetic. And the other beauty of place value is that since we only have digits going from 0 to 9, it means that whenever you're adding, you're never adding more than two numbers at a time, one of which is a digit between 0 and 9, which means you can count on your fingers. Thanks to place value, you can actually do arithmetic counting on your fingers. In fact, let's explode the counting on your fingers myth once and for all. Remember they say, don't count on your fingers? You can't count on your fingers. What if the numbers are too big? It doesn't matter. In fact, let me do this problem the completely mechanical way, the rote method, without worrying about the logic behind it. I'm going to make a comment about that in a few minutes. We start to add. We say 6 plus 9 is 15. How do we get that? Well, we got that from the tables. All right, what's 15 plus 3? Well, that's not in the tables, but we can say what? 15, 16, 17, 18. And then we said what? Put down the 8 and carry the 1. And then we said 1 and 8 are 9. Still got that from the tables. 9 and 5 are 14. 14 and 7 is 21. Put down the 1 and carry the 2. I'm just reciting this the way I was taught. 6 and 9 are 15. And 2 is 17. And 2 are 19. Put down the 9 and carry the 1. 1 plus 5 is 6. Plus 2 is 8. Plus 1 is 9. Notice how you can do this problem just by counting on your fingers. And again, let me emphasize that what you really want to be saying here is 3 ones plus 9 ones is 12 ones. 12 ones and 6 ones are 18 ones. And then even though you're mechanically just saying, I'll put down the 8 and carry the 1, what you're really saying is, I'll write the 18 as an 8 and one more 10, etc. One more thing that comes up here that's kind of interesting. I did something that wasn't covered by the rules. Did you notice that all our rules talk about how you add two numbers? And here I'm adding 3. Well, that's where the associative property comes in. It says when you're adding three numbers, you can group them any way you want. And so what that means is, even if you're adding a big chain of numbers, at any one time, you're just adding two of them. When you say how much is 1 plus 2 plus 3 plus 4, you're saying 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10. Okay? Now, what I wanted to point out was, is there anything wrong with teaching this algorithm? I learned it that way, and the answer is there is nothing wrong with it. What's wrong is if the student learns it just by rote and has no feeling for what it means. Now, I don't know which way you're more comfortable. I don't even know in my own mind which is the better way. For example, is it easier to start by showing the student the rote method so that they get the hang of it and then say, here's the logic behind it? Or is it better to say, let me show you logically what's happening and then we'll show you a shortcut? Let me be more specific about that. Let's revisit this problem and now do it what I would call the logical way. 6 plus 9 is 15, plus 3 is 18. 18 is 18 ones, which is the same as 1 10 and 8 ones. So what I'll do is I'll write the 8 in the ones place and trade in 10 of my ones for a 10. Now I'll do the same thing here. 8 plus 5 is 13. 13 plus 7 is 20. 20 what? Well, they're all modifying tens, so I'll write the 20 by keeping none in the tens place and 2 in the hundreds place. Now what do? I add the 2 and the 9 to get 11, and 6 is 17. 17 what? 17 hundredths. So the 7 goes into the hundreds place, the 1 goes into the thousands place, and then I say 6 plus 2 plus 1 is 8. I'm sorry, 5 plus 2 plus 1 is 8. And now I have what? 18 ones, 20 tens, 17 hundreds, 8 thousands, and I add these up. And in effect, what I've really done is I didn't have to put the 0 in here because the 9 was holding the tens place, but this is what we really did. Now we can say to the student, look, I didn't have to put the 2 down here, I could have put it up here. And I didn't have to put the 1 down here, I could have put it up here. And what that would do is, it saves me 3 lines. But by doing it this way, the student sees clearly what it means when you say, put down the 8 and carry the 1, put down the 0 and carry the 2, etc. And we see we have what? 8 thousands, 9 hundreds, 110, and 18, and 8 ones. Okay? Now, the next thing that comes up, which is I think interesting to talk about, is have you ever heard any of your students say things very happily, I could do everything except the word problems? That's a terrible admission in terms of learning anything. Because you see, in the textbook of life, there are only word problems. In other words, nobody comes up to you and says, I don't think they do, comes up to you and says, how much is 287 plus 369? However, there might be a word problem that says John has 679 marbles and Bill has 298 marbles. What is the total number of marbles they have? Notice that in stating that problem, no one is telling you what to do. They're asking you a question. You have to say, oh, to find the total, I have to add the amount one has to the amount the other has. Now, what the calculator will do for you is it will do the addition. It won't tell you what to add. In other words, again, the calculator is a very wonderful tool for helping relieve the burden of computation. But the more it relieves the burden of computation and the more time you have to analyze a problem, the more important it becomes to be able to translate the given information into something the computer can compute for you, the calculator can compute for you. So we say, okay, I'll take the number of marbles that John has and the number of marbles that Bill has, and I'll add them up. 9 and 8 is 17, 9 and 7 is 16, and the one I carried is 17. 2 and 6 is 8, and the one I carried is 9. And so the answer is 977. Again, notice the beauty here. You had to know what you had to do, and then the calculator could do it for you. Now, is it possible that a youngster has trouble dealing with numbers like this and carrying? And the answer is, if so, Look what happens by visualizing this problem. Suppose all I was given was this problem here, and I wasn't given the word problem. Well, by thinking in terms of the word problem, I come up with what's called the same sum technique. What that means is this would have been a much easier addition problem if the 298 had been 300. Well, that's an easy thing to do. All John has to do is to give Bill 2 of his marbles, which means that John has 2 less, but the total number of marbles hasn't changed. In other words, if you have 2 groups and you take some from one group and put them into the other, the number in each group has changed, but the total number hasn't changed. Remember what we said. The number of tally marks in a group doesn't depend on the order in which they're written or in how they're arranged. Okay? So if I do this, let's see what happens. John originally had 679 marbles. He gave 2 to Bill, so he now has 677 marbles. Bill originally had 298 marbles, but now he has the 2 that John gave him, gives him a total of 300. So the total number hasn't changed. So how many marbles do they have altogether? 677 plus 300. And notice how much simpler this looks than this. And by the way, in pure mathematics, they wouldn't use a model like this. What they would say is, look, we added 2 and subtracted 2, so in effect, what we did was we added 0 to the total amount. My feeling is that if you do the problem this way, and then you say to the student something to the effect, plus 2 minus 2 adds up to 0, they'll see where it's coming from. But at any rate, that's enough from the point of view of giving you new information. Let's go now to our practice problem. And the practice problem will emphasize the same sum technique because I think that may be relatively new to some of you, but it's a wonderful way not just to show students a shortcut to doing arithmetic problem, an addition problem, but also to get them to look forward to doing drill. In other words, you give them a problem that would be rather cumbersome to do in the form that it's in, show them what they will perceive to be a trick, but in reality is some serious math, where you reduce that problem into a simpler but equivalent problem, and they will then check to see if the easier way really gives you the same answer as the more complicated way. So with that in mind, let's turn our attention to the practice problem. And I remind you again, you pause the tape as you look at the practice problem, do the problem. After you do the problem, then you resume the video and look to see what my solution was and what comments, if any, I make about the solution. So here's the practice problem. It says, use the same sum technique to compute the sum 297 plus 576. And you see, to compute that sum, you say the problem would be much easier if the 297 was 300. So what I'll do is I'll take 3 away from the 576, leaving the 576 as 573, add the 3 onto the 297, making that 300. Notice again what I've done mathematically. I've added 3 and subtracted 3, so in effect I've done nothing. But this sum is the same as this sum, and very easily we get the answer 873. And a student might say, well, couldn't I have made the 576 600? And this again is an illustration that in many times, even though there's only one right answer, there's not only just one right way to get the answer. You could have said, okay, I will make the 576 into 600, but to do that I have to add 24. But if I add 24 to the 576, I have to subtract 24 from the 297 to keep the sum the same. So the 576 becomes 600, the 297 becomes 273, and the sum is still what? 873. Well, now the youngster has done the problem in possibly 2 different ways, each of which is probably simpler than doing this problem here. My guess is this is the way they would choose to do it. But then where the fun would come in is to say, does this really give you the right answer? And they would say, let's do it the traditional way. 6 plus 7 is 13, put down the 3, carry the 1. 1 plus 9 is 10, plus 7 is 17, put down the 7, carry the 1. 5 and 2 is 7, and 1 is 8. And they see it's the same thing. And now what was tedious drill tends to become a bit of fun. At any rate, that completes our session for today, and I look forward to seeing all of you again next time.